Check 1, 2. Oh, there I am. Okay, great. Sorry about that. I had a little bit of a glitch getting connected, but today I have some things to present and also my normal Monday production tasks. So let's dive right in because I don't have a ton of time today. I need to get ready for a 9 a.m. meeting. But yeah, I thought I would kind of practice presenting this Audio 101 presentation that I slapped together last week. Should be very informative. We'll go through a lot of topics that not everyone needs to totally wrap their head around 100%, but I wanted to at least have the information presented in a way that, and I'm sure I kind of want to change it before I make it like a regular thing. So I don't know. I'm just kind of rambling about stuff. So let me just go ahead and dive right into the practice presentation. Let me make sure I got my camera set up. Oh yeah, you're just looking at me. So press this button. Is it working? There it goes. Awesome. Yay. Oh, there's like animations and stuff. See, I haven't even practiced this at all. So welcome. My name's Sean Ashcraft. I'm going to be presenting audio basics topics today. And let's see what happens if I... Oh, see, this is a really quick crash course in audio for public broadcasting. Yeah, so, okay, this one does not have animation. All right, fine. That's fine. So the stuff that the top points that we're going to hit on today, we're going to explore what audio is, first off. Got to get some basics down. What are some tools that we use to do the audio? And what do I need to know as somebody who is an audio person or is working with audio? What do I need to know about audio quality and summary? Summary? What is that? Audio quality summary. I don't know. Don't look too closely at this presentation. It's got a bunch of text on the screen because I like writing out my thoughts. Because some of this stuff you do have to be kind of careful about the details, in my opinion, if you want to be presenting about it. So anyway, what the heck even is audio? So I just grabbed the simple, like we're going to the basics here, just grab the simple Wikipedia explanation of what audio is. And that is that it refers to sound as it is transmitted. Suddenly I can't read. As it is transmitted in signal form. So when we're talking about audio, we're specifically talking about signals that represent sound. So audio is not necessarily the same as sound. They are two forms. Audio is a representation of sound, basically. The signals that can create sound. So what exactly is sound? Like, have you ever stopped to think, like, I'm somebody who hears things all the time? What does hearing even mean? Well, it has to do with the change of air pressure over time. That's what sound is comprised of, kind of like these squigglies on this picture that Microsoft PowerPoint suggested that I use. So it's these, differences, this change in air pressure at certain frequencies. This is what our ears hear and perceive as sound. It's what these change in air pressure levels. That's what a microphone measures or senses. And that's what speakers, like my mouth, is a form of a speaker, sort of, with my throat and all of the vocal cords and everything. But also computer speakers or loudspeakers or even headphones are just tiny little speakers. So, and I'm talking into a microphone. So there we go. We covered, here are the really, really basic things when we're talking about audio. Okay, so let's just dive into a little bit more detail about the endpoints, the technology that we kind of interact with a lot. So you got your microphones. This is what's called a transducer that just converts this particular kind of transducer converts air pressure energy into electrical energy. Just really simplifying that there. Specifically, most microphones, like 99.9% of microphones, they create a tiny little analog signal. So I'll just kind of leave it at that. I'm not going to go too much deeper at like what comes after a microphone, but that's what a microphone basically does. And it's pretty neat how they work, but I'm not going to, like I said, I'm not going to go into too much detail here. Something that's interesting about microphones, they might be hanging out in one point in space, but they can be built in such a way that they can have directionality. Now, this makes sense to us because we have ears that are shaped a certain way, and we understand if we turn our head, we get like a different perspective on the sound because we're hearing the sound come from different directions, depending on where our head's placed or where the sound is coming from. So microphones work the same way. They a plain vanilla microphone, you stick it in the middle of a room, it actually most microphones will actually be able to pick up sound from all directions. So some microphones, like this one that I'm talking into, just picks up in one direction. It's built in that way. So by that, I mean, like, if I hang out back here, you can hear how it's got like a completely different sound. Like, it's way off axis is what audio nerds call it. And then just something else that's interesting is that the signal that they create is really tiny, like in the millivolt range, very low current, because there's not a lot of energy. We're talking like conservation of energy. There's very little energy that moves, the properties of the transducer that microphones create the sound. So anyway, let's go on to the opposite of a microphone, which is a speaker. Fun fact, you can actually some speakers you can use as microphones. You can't, things that are made to be microphones, if you try to use them as a speaker, you'll probably destroy them. But a speaker is a transducer that creates sound waves from usually a higher powered analog electrical signal. So much like a microphone, it only creates sound in one point in space, and it needs a kind of hefty power to move the voice coil to get the speaker to move. So that's a whole thing. Power level is much higher than what microphones create. So that gets into the details of all the stuff in between microphones and speakers, which is audio. So that's my little preamble on what sound is and the edges of the audio sphere of media. Like if you imagine, you got your visual stuff and you got your audio stuff. Audio stuff is audio because it interacts with sound. So here's the overall signal flow that we just talked about. People make sound, or nature, or whatever. That's picked up by microphones. You got your low-powered audio that needs to be processed into high-power audio, which then can go to speakers that people can hear the sound that it makes. And media also refers to how it can be stored and routed. So I kind of threw in the middle here, not only does audio get processed, it also gets mediated. That's not a verb, but yeah, it's just kind of fun thinking about audio is the stuff here in the middle. So what kind of audio signals are there? Well, there's like 5 million different types of audio signals, but the two basic types that we tend to use, the way that it's typically carried over media, is two forms, either analog or digital. There's like the two major types that we work with, and most audio, even if it's digital, that digital audio is just a representation of an analog signal. Most speakers are not digital speakers. The way that they would be digital, or microphones for that matter, the way that they would be digital is by instantly converting air pressure to digital sounds, which is not really a thing. Like even in like our phones, the little speakers and the microphones, even despite how small they are, those little transducers that are in those devices don't instantly like create a digital signal. At least not that I'm aware of yet. I would say most digital devices first work with an analog signal. So, but yeah, just making sure we understand the difference between analog and digital real quick. Analog, the signal is kind of proportional to whatever we're measuring. So if this is the change in air pressure, the sound pressure level, whatever, an analog signal would be basically a copy of that in a different media. So, it'd be the electrical fluctuations or the changes in voltage, or maybe the change in current through copper wire. And magnetic tape, that's the magnetic flux is what's changing. What's the change in the magnetic field that's interacting with the tape and all the iron particles that are on the tape. Tape is weird. And if you think tape is weird, optical or sound on film is even weirder. But we won't go there. Over the air, radio, that's what we work with in radio. We do radio stuff. There's other analog types, grooves and vinyl, and there's all kinds of other stuff too. But digital is the binary representation of that. So basically I'm not going to go into sample rates and all that stuff today, but basically we take a little sample of the analog signal at basically one point in time, and we just do that really, really fast. So you get kind of instead of you get like a series of values. So like this is small, and then this is pretty big, and this is very big, and so on and so forth. So digital media, what's interesting about digital media is that all analog formats, as long as they have enough bandwidth, they can carry digital signals. So that's something that's kind of crazy. It's not even really that crazy, but like you can send digital signals over copper wire. You can put digital signals on magnetic tape. That's how computers kind of used to work, and some storage systems still use magnetic tape. You can optical, those are CDs. You can send digital signals over the radio, so that's what RDS is. You can, if you really want to, you can put digital signals on vinyl records. Not recommended, but then the digital media world opens up to an entirely new type of media that's specifically for digital media. Like it's like created to store digital media and not created specifically for analog. It wouldn't do very well for analog media. You might be able to make it work if you packetize or whatever the analog, like if you chop it up. But anyway, so digital media typically it has stuff like optical discs, like CDs. Those are starting to go, kind of more specialized stuff, I guess. Hard disk drives are most of our hard disk drives are optical media, so it's kind of redundant. But solid state disks, like transistors, maybe quantum, when that gets like a little bit more common, maybe we'll see some like quantum storage, things. And then I wanted to mention, since I mentioned up here copper wire and over the air, which are like transmission media, I wanted to mention packetized networked media. So if that's like USB or like local, connections, those are usually like data link, this device is connected to this other device and they can share digital information between each other. but also over the internet. Cell networks are basically the internet, and then cloud, which is, you can have a distributed media system, which kind of blows people's minds. But it's how stuff like Netflix and that kind of stuff work. So let's dive in a little bit further, but not too deep. Like I mentioned, I pulled this from Wikimedia, and I just thought it was a lot of fun. So I wanted to throw it into my lame PowerPoint. But when you add the digital world, this is basically the signal flow when you start thinking about digital media. So you got your real world, you got your people. Like I said, I thought this was just a fun, thanks Teeks99. So sound waves, they happen. Microphones, like we talked about, create little voltage. And then we have this new thing called an A to D and a D to A converter. These are analog and digital converter interfaces, basically. And so they basically, like I said, with digital media, just samples really, really fast the analog signal so that you have a binary representation of that. This type of media is really great for processing in a computer and sending it over different types of media. So I love how they have this old school iPod on here. But you can also think of any other I/O devices. So that, I wish they had another arrow here pointing to like a computer network, like the internet, or a cell network. So that's kind of how, cell phone calls work. They pick up the sound from nearby your phone or like next to your phone, and then the microphone picks that up. Even if it's just like a short, going from the analog to the digital, or maybe it's all on one chip. Even, this might be tiny little technology built into the computer. But yeah, it converts it to digital and then sends it over the network. And then other signals come in from the network and then get sent out the analog, or the digital to analog converter, and then out to your ears to hear. This, I did want to dive to this level really quickly, and that is the von Neumann architecture for computers. Basically, it is just saying that computers, this is what computers are. It's what I'm trying to communicate here. Computers have input and output devices. So, you think in terms of audio, microphones and speakers, I guess. And then inside of the computer has, your CPU, your processing, basically. And then it has interaction with memory. So storage, whether that's long-term storage or short-term fast memory. And these input and output devices are controlled by the computer, so they don't necessarily need to be audio devices. They can be network devices or digital devices of other kinds. So I wanted to kind of crash course through digital audio formats, because when you're working in media, you're going to have people all the time be like, hey, this is the format that we're working with here. But these are the most common formats that can work basically anywhere. So even if you're working in a very specialized system, like, I don't even know, like you go to like some super high-end studio and they only have direct sound stream stuff, and it's like, the range of human hearing only goes up to 20K on average, but then they'll have stuff that goes to like, 192K, just stuff that's crazy. But anyway, here's the main digital audio formats. We've got lossless and linear formats. This just means that regardless if you can hear the signal, it's going to record the signal. It's just, here is the bit stream, like the straight up, like here's all of the digital information, whether you want it or not, basically. So Wave and Apple's audio format, pretty typical. Wave's more common with broadcasting. Then the sample rate, so these are like some dimensions of these formats. So when you're working with Wave or other lossless formats, the thing that really determines how high quality your audio is the sample rate and the bit depth. So basically if you got more samples, you can hear more frequencies in the audio. That's kind of the idea there. So again, this is roughly the range of human hearing, 20 hertz to 20,000 hertz. Those are the frequencies we could hear. I'm not going to talk about what frequencies are and stuff. And then there's this theorem that says that if you want to be able to capture this range of frequencies, you need at least double your highest frequency. And some other stuff, like maybe you want even a little bit more so that you could filter it, okay, without aliasing, but I'm not going to go into all that stuff. So that's the reason why most sample rates are usually around 40K, maybe 48K is kind of like reasonable standard. So that, how many frequencies can you sample is basically what's going on there. And then bit depth is how much fidelity, whenever you are sampling, how precisely are you sampling that level? So the more bits, the more signal that you can get with the noise. So with audio, there's always going to be noise, sometimes called the noise floor. This is like just the quietest thing, the smallest possible signal that you could have. And so the more, the more that you can pack into your samples, the more signal you can capture, and the noise can stay down here. 16 bits is kind of like, that's fine. 96 dB of audio dynamic range. It's somewhere around there. I don't know if that's exactly what it is, but that just means, so if you compare that to normal human dynamic range, I think sound pressure level, I think 0 dB is like nobody can hear 0 dB, basically. It's too quiet. But it's just on the edge of like not actually being possible to hear. And 100 dB is like a pretty loud rock concert. And then 120 dB is like the loudest rock concert you've ever been to. So 96 dB, it's not the most amount of dynamic range that will ever be required and that humans could ever hear, but it's everything that you're gonna need. So that's roughly, that's pretty good. And then you have lossy format. So we just talked about lossless. Let's talk about lossy. This stuff like MP3s, AAC, M4A are becoming more common. Basically, digital media is kind of like slowly becoming one kind of format, even though there's millions of formats out there. But this is the Moving Picture Experts Group, whatever. I don't remember what all this means. But the big thing here is bits per second. That's how big the compressed audio stream is. And basically the bigger the bits per second, the more bits per second you have in your compressed format, the more audio is preserved. So that's the big thing to take away there. So when it comes to delivering media for professional stuff, there's usually two endpoints. You either are delivering something that's still in production phase, so it's still like we're still processing it, we're still editing things together. So most of the time we're still deciding how to distribute the format. For these, situations, you kind of want a big production format, something high quality that preserves all of the original audio details. So go ahead and use .wave. .wave is just a wrapper. It's just like, here is how you put headers on the data to say, hey, I'm this kind of data. The data itself, it's a type of data called pulse code modulation. It's basically just binary, like the most simple kind of binary you could think of. So these are the kind of the standard, like, this works great for production. 48 kilohertz sampling rate. CDs are 44.1, so it just gives you like a little bit more wiggle room on your filter. 24 bits per sample. Usually it's more than plenty. That's like 120 or 140 or something. It's like a crazy amount of dynamic range available in the format. So these create big audio files that don't lose any audio detail. And one thing I'll say about production formats is you want to keep all these details because you don't really know if you're going to turn up the audio or turn it down or process it a certain way. So you kind of want to have all of those details in there so that if you got like really quiet audio and you need to bring it up, and even if there is a little bit of background noise, you don't want that to all be digital and gross. So when you turn it up, you can hear even more of that background detail that maybe when you're recording it, you're like, I don't know, we're not gonna be able to hear this sound. But then once you process it and decisions are made, you might be like, oh, maybe I do want that sound. Like I want that bird chirp, or I want this ambience or whatever. So that's why audio quality really matters at the production level. Because it just, you capture everything that you need, and then later you can decide to get rid of what you don't. So, there's Stan. I'm just going to stop this.